Generating maximum thrust requires the controlled acceleration of mass. Rocket thrust, the reaction force, is precisely quantified by the equation F equals mass flow rate times exhaust velocity plus the pressure differential term, F equals m dot times V sub E plus P sub E minus P sub A times A sub E. The momentum thrust term, m dot times V sub E, fundamentally dictates rocket performance. Liquid fuel engines are engineered to maximize exhaust velocity, V sub E, by efficiently converting the thermal energy of combustion products into kinetic energy. High chamber pressure, P sub C, is essential because it directly dictates the maximum achievable expansion ratio and thus the maximum theoretical exhaust velocity. The primary engineering challenge is the simultaneous maximization of the mass flow rate, m dot, while achieving the highest possible V sub E through optimal thermodynamic expansion. This balance defines the engine's power density. Specific impulse, designated I sub s, measures engine efficiency, defined as the total impulse generated per unit weight of propellant consumed, typically expressed in seconds. I sub s is directly proportional to the effective exhaust velocity, V sub q. The Tsiolkovsky rocket equation demonstrates that the final velocity change, delta V, is proportional to I sub s and the natural logarithm of the vehicle's mass ratio. Maximizing I sub s requires two primary thermodynamic conditions: minimizing the average molecular weight, m, of the exhaust products, and simultaneously maximizing the combustion temperature, T sub C. I sub s performance is fundamentally limited by the square root of T sub C divided by m. This relationship emphasizes the necessity of producing light exhaust molecules, such as water vapor from hydrogen and oxygen combustion, to achieve peak efficiency. The combustion chamber functions to convert the chemical potential energy stored in the propellants into thermal energy at extremely high pressure, P sub C. Characteristic velocity, C star, quantifies the efficiency of this energy conversion process, independent of the nozzle geometry. C star is defined mathematically as the chamber pressure times the throat area divided by the mass flow rate, P sub C times A sub T divided by m dot. Achieving high C star requires complete, stable combustion and minimal heat loss within the defined chamber volume. The combustion process is thermodynamically modeled as an adiabatic, constant pressure process, maximizing the enthalpy change, delta H, to produce the highest possible temperature and pressure gases. The mixture ratio of oxidizer to fuel, O over F, is often optimized slightly fuel-rich. This strategy maximizes I sub s by lowering the average molecular weight of the exhaust, accepting only a minor reduction in the maximum theoretical combustion temperature. The DeLavo nozzle is engineered to convert the thermal energy of the high-pressure combustion gas into directed kinetic energy. Gas accelerates subsonically in the converging section, reaching Mach 1 exactly at the throat, A sub T. It then expands supersonically in the diverging section. This expansion is ideally isentropic, meaning the entropy of the gas remains constant throughout the process. The thrust coefficient, C sub F, measures the effectiveness of the nozzle in converting chamber pressure into usable thrust. C sub F depends primarily on the expansion ratio, A sub T over A sub A, and the ratio of heats, gamma. Optimal thrust occurs precisely when the exit pressure, P sub E, equals the ambient pressure, P sub A, defining the engine's design point. Any condition resulting in underexpansion or overexpansion significantly reduces the overall thrust efficiency. Combustion temperatures routinely exceed 3,500 Kelvin, necessitating active cooling systems to maintain the structural integrity of the engine walls. Regenerative cooling utilizes the cryogenic propellant, such as liquid oxygen or liquid hydrogen, to absorb heat from the chamber and nozzle walls prior to injection. The coolant flows through precisely milled channels within the engine structure, acting as a highly efficient heat sink. This process simultaneously preheats the fuel, slightly improving its energy state before it enters the combustion chamber. Heat flux is highest specifically near the nozzle throat due to the combined effect of high gas velocity and extreme temperature gradients. Film cooling, which involves injecting a thin layer of propellant along the inner wall surface, supplements regenerative cooling in critical high heat areas to prevent material failure. Propellant selection dictates both the achievable specific impulse and the overall engine density. High-energy combinations, such as liquid hydrogen and liquid oxygen, yield the highest I sub S because the resulting exhaust product, water, has an extremely low molecular weight. Conversely, denser propellants like kerosene, designated RP1, combined with liquid oxygen, offer lower I sub S but possess higher bulk density. This higher density results in smaller required tank volumes and consequently reduces the structural mass of the launch vehicle. Hypergolic propellants ignite spontaneously upon contact, simplifying the ignition system significantly, but they often exhibit lower performance metrics and higher toxicity. The final propellant selection balances the mission's required velocity change, delta V, against constraints related to vehicle size, system complexity, and operational safety requirements. To achieve the necessary high chamber pressure, often exceeding 20 megapascals, propellants must be mechanically pumped against this massive pressure differential. Turbopumps, driven by a dedicated gas generator or integrated into a staged combustion cycle, provide the required mechanical energy input. The pump work required is directly proportional to the volumetric flow rate and the pressure rise. W equals V times delta P. The efficiency of both the turbine and the pump directly impacts overall engine performance, as the energy utilized to drive the turbopump is necessarily diverted from the main thrust stream. Staged combustion cycles maximize efficiency by burning only a small portion of propellant to power the turbine, then injecting the resulting hot, high-pressure exit into the main combustion chamber for complete high-performance combustion. Chemical rocket efficiency is fundamentally limited by two factors: the intrinsic energy density of the propellant chemical bonds and the maximum temperature that engine materials can structurally withstand. The theoretical maximum specific impulse for conventional chemical systems is approximately 500 seconds. Future improvements focus on optimizing combustion stability, reducing turbopump mass through advanced design techniques, and utilizing materials like ceramic matrix composites, CMCs, to tolerate significantly higher combustion temperatures. Aerospike nozzles offer altitude compensation by continuously adjusting the effective expansion ratio, potentially increasing the average thrust coefficient across varying atmospheric pressures, thereby improving overall mission performance.